Electric flux through a cube. The cube in the figure has sides of length L equals 10 centimeters. The electric field is uniform, has magnitude E equals 4 10 to 3 newtons per coulombs and is parallel to the xy plane at an angle theta of 53.1 degrees measured from the positive x-axis toward the positive y-axis. So it's going to be measured with respect to the positive x-axis pointing towards the positive y-axis. So that's about the direction of the electric field. Part A, what is the electric flux through each of the 6 cube faces? S1, the left side, S2, top, S3, right side, S4, the bottom, S5, the front, and S6, the back face. And part B, what is the total electric flux through all faces of the cube? Okay, so as I said, the electric field has to be in such a direction that it is parallel to the xy plane and making an angle 53 degrees, so that's more than 45, so it will be beyond this diagonal here with respect to the positive x-axis. And here we have the area vectors for each face pointing out. So if I look at these area vectors, the A1 area vector is this one, so that's pointing in minus j hat direction. So the area is L square, so it's going to be minus L square j hat. The second area vector, A2, let's take a look at this. That's the top face, so that's pointing in plus k hat direction. So that is L square plus k hat direction. Area vector 3, that's this right side here, that's pointing in plus j hat direction. So it is L square j hat. Area vector 4 is for the bottom one, which is pointing in minus k hat direction. So that is minus L square k hat. Area vector 5 for the fifth face, that's the front face here, so that is pointing in plus I hat direction, L square I hat. And area vector 6 for the sixth face, which is the back one, is pointing in minus I hat direction. So this is minus L square I hat. Okay, so it is minus L square j hat, L square k hat, L square j hat, minus L square k hat, L square I hat, and minus L square I hat. On the other hand, the electric field has an x component, E cosine theta, that is in I hat direction, and it has a y component, E sine theta, in j hat direction. So the flux phi 1, which is through face 1, is the dot product of the uniform electric field with the area vector A1. So that's going to be, because A1 is in minus j hat direction, we have the y component coming into play, minus E L square sine theta. Why minus? Because this is in j hat direction, this one is in minus j hat direction. The flux through phase 2, phi 2, now the area vector is in k hat direction, dot product with the I hat and j hat is 0, so electric field dot the second area vector is 0. The third phase has a flux. This is L square j hat, so E sine theta L square j hat. Electric field vector dot product with the third area vector, which is E L square sine theta. The fourth phase, phi 4, is in, again, minus k hat direction, so the dot product will give me a 0 here. electric field dot product with A4 is 0. For the fifth phase, phi 5, I have electric field dot product with A5. The A5 is in L square I hat direction, so the dot product will give me EL square cosine theta. And for the sixth phase, phi 6, I will have electric field dot product with the sixth area vector, which is minus E L square cosine theta. All right, so that's going to be the flux through all of these phases. Now, if I substitute numbers here, theta is equal to 53.1 degrees. So sine theta is 0.8, cosine theta is 0.6, L is 10 centimeters, 0.1 meters. The electric field magnitude is 4.0, it was 4.00 times 10 to 3 newtons per coulombs. So if I substitute these numbers here, for phi 1, I will have minus EL square sine theta minus 4 times 10 to 3 times 0.1 square times 0.8. For the second one, phi 2 equals phi 4, I have 0 Newton meter square per coulomb. So that's the answer for the second and the fourth phases. And then for the third flux, phi 3, I see that phi 3 is equal to minus phi 1. So it is minus phi 1. So substituting these numbers here, 4 times 10 to 3.1 squared times 0.8, we obtain 32.0 Newton meter square per coulomb for phi 3 and phi 1. And for phi 5, the flux through the fifth phase, I have 4 times 10 to 3 electric field L square 0.1 square times cosine 53.1, 0.6, and I find that phi 6 equals to minus phi 5 equals to minus 24.0 Newton meter square per coulomb. That's the flux. Now in part B, we're supposed to calculate the total flux. So sum over I, 1 to 6 phi I, the total flux, is flux 1, which is minus 32. So you can see here, this is the negative 1, minus 32. Flux 2 is 0. Flux 3 is plus 32. Flux 4 is 0. Flux 5 is plus 24. Flux 6 is minus 24. Therefore, we find that the total flux is 0 Newton meter square per coulomb. All right. So what is the total flux? It is 0. Why is it 0? Because it doesn't contain any charge. So according to Gauss' law, when the charge enclosed is 0, the total flux through this cube should be 0, and that's exactly what we find by this explicit calculation. Okay, so in this problem we talked about the electric flux through a cube which has 6 faces, And for each phase, we have looked at the area vector, and we take the dot product between the uniform electric field and the area vector to find the flux through that phase. Obviously, phases 2 and 4 do not have a contribution because the electric field is on the xy plane. It's parallel to the xy plane. And for the other two, we find that the fluxes through phase 1 and 3 cancel, and phase 5 and 6 cancel, and we find a total flux of 0. When we substitute the numbers, it is 32 and minus 32, 24 and minus 24, 0 and 0 Newton meter square per coulombs. So this result that the total flux is 0 is consistent with Gauss law because the total charge enclosed by this cube is 0.